start by opening the cross-section View Assistant. Here, we can select a pre-created template to create our prototype. We will choose Routing with Shielding. When a template is chosen, a prototype graphic shows the cross-sectional view of the data lines and shielding. Here, 5 metal layers are used. The blue shows the signals and the green the shielding. In the small editor window, you can easily change the parameters such as the offset, distance, route thickness, and the number of signals represented. Any changes you make are shown immediately in the preview window. Next, we enter the length of the nets for our prototype. We will select 300 microns. With this information, now we can create S-parameter plots based on our model using the Synopsys HFSS extraction engine. We can plot crosstalk and insertion loss magnitudes based on operating frequency. The results are dependent on the shielding pattern selected. We have a built-in library of common shielding patterns, and engineers can modify or create their own. Next, let's look at an eye diagram of our prototype routing structure. If it's unacceptable, we can modify the HBM configuration and rerun. Now that we have an acceptable HBM routing prototype, let's perform automated die-to-die routing. Here, we're looking at the standard JEDEC HBM bump pattern on a silicon interposer. To perform auto routing, we open the Task Assistant and open 3D channel routing under interposer routing. In this dialog box, we just fill out the data for our routing, such as the layers we want to use, in this case, metal 4 and metal 2. We select the routing mode as HBM, and we also specify the channel boundaries for the routing. It can be specified with fixed coordinates, or we can draw a box for the boundary. We also specify a pattern file. This contains the constraints and the parameters for the route. Then we enter the desired wire width and spacing for the routes. A preview of the resulting tickle command is shown below. Applying the command, we see the resulting auto routes with 45-degree bends. Zooming out, we see all channels routed, bumps connected with routes and vias added. Zooming back in, we see the detail of the 45-degree signal routes. We can also see that shields have been added, and we zoom into the area and turn on the shielding layers, and we see that the shielding follows the signals through the 45-degree bends. Here we turn on M1 and M4 to show the shielding and the signals. Next, we'll demonstrate electromagnetic extraction using HFSS. The 3DIC Compiler Task Assistant simplifies the extraction setup. We enter the basic data such as the stackup file, the adaptive frequency, and other information. We enter the range of frequencies for the sweep. The command at the bottom shows the resulting tickle command that will be run. Now we will set up the extraction. We select the physical region for the extraction by drawing with the mouse. All of the available nets in the region are shown on the left. We can now select the nets we want to extract, and they will be highlighted in white. We can also select the nets using a filter, and providing those nets will automatically create the region for the extraction. Set the VSS ground net as reference, and the selected nets will be extracted using HFSS. Selecting Skip Solve will build the project and show a preview, but won't actually run the extraction. This lets us check what will be extracted first, making sure the layout and the ports are correct before we run extraction. Now we can launch the extraction. The HFSS run log is displayed in the console window. When the extraction is complete, we can view reports such as worst insertion loss, skew, and worst near-end and far-end crosstalk magnitudes. On the right is a histogram showing insertion loss ranges, along with the number of nets in each range. Now that we have an extracted HBM routed design, let's look at design optimization using AI and ML. We can use 3DIC Compiler's built-in AI engine to find routing parameters that will maximize throughput and minimize far-end and near-end crosstalk. The chart on the upper right shows our solution space. On the left side, we have low crosstalk, but the transmission is too low. On the upper right, we have high transmission, but the crosstalk is too high. The purple area contains the acceptable solutions, and we will use AI to find an optimal solution for our prototype. We open the AI viewer and see the metrics charts on the left and the runs with all the run data on the right. Here, we can see all the changeable parameters, such as wire width and pitch, and shield width, as well as the pattern. Let's look at all the run data points, with the baseline run marked in the center. You can see the worst near-end crosstalk plotted versus the worst insertion loss. We can apply different criteria to determine the best design. Going to our runs chart, we can see all the data run for each run and can sort the table by any parameter. Let's summarize what you've seen today. We perform prototype HBM route planning with cross-sectional analysis, routed HBM to SoC signals with 45-degree routing, ran electromagnetic extraction using the Synopsys HFSS engine, and optimized the design using both AI and ML, all from within the powerful 3DIC compiler platform. This concludes our demo, and thanks for watching.